With the classifications and principles covered, we would like to look at examples and applications of chemical sensors. As we all know, glucose is the most basic and important energy source of human daily life, and as such, glucose monitoring is essential to keep people healthy. The determination of glucose concentration in blood is clinically important to people with diabetes. Diabetes is a metabolic disorder where fluctuation occurs in the normal blood glucose range. According to the International Diabetes Federation, it is estimated that the number of people suffering from diabetes will reach 592 million by 2035. Glucose monitoring is also essential for other human health reasons like optimizing athlete performance, and it is also integral in the design of glucose-based fuel cells. Glucose sensors were categorized according to the following in the literature. In this presentation, we would like to focus on continuous monitoring sensors. Our blood glucose level fluctuates regularly, and it fluctuates depending on factors such as food, exercise, and insulin. And up until now, we were only able to measure blood glucose level at a specific point using point sample glucose sensors. Now, we can continually and thoroughly monitor glucose levels all day and night using continuous glucose monitoring technology. This continuous glucose monitoring sensor is responsible for measuring the glucose in the interstitial fluid, which is the surrounding tissue fluid. It is important to note that the blood glucose level, denoted as Bg, is not the same as the glucose level read by the sensor from the interstitial fluid, but it can be estimated from this value. Non-invasive continuous monitoring methods have been at the forefront of advances in glucose sensing, as they offer painless and safe alternatives for measuring blood sugar. They also offer protection against risk of possible infection due to traditional methods such as finger pricking. Due to the limited scope of this presentation, I'll only elaborate on why fiber optic chemical sensors are commonly used in this category of glucose monitoring. Fiber optic chemical sensors are used due to several optical properties being directly related to the glucose concentration, and this allows it to be measured directly using fiber optic technology. We'll be further discussing these properties. As you can see, the relationship between the refractive index and glucose concentration is highly linear, and you can see it's highly correlated as well. Examples of sensors that are based on this relationship are the small U-shaped bending induced interferometric sensor and the surface plasmon resonance based sensor, respectively. As you can see the pictures of this type of sensors below, and this is some extra information on this type of sensors. Near-infrared spectroscopy is a widely known non-invasive method that is based on focusing a beam of light on the body in the 750 to 2500 nanometer spectrum. It allows glucose measurement in tissues in the range of 1 to 100 millimeters of depth. The light focused on the body is partially absorbed and scattered due to its interaction with the chemical components within the tissue. This phenomenon is known as an attenuation of light in tissue, and it is described according to the light transport theory, which can be mathematically depicted by the following equations, where I is the reflected light intensity, I subscript 0 is the incident light intensity, UEFF is the effective attenuation coefficient, and D is the optical path length in the tissue. The effective attenuation coefficients can be further expressed by the absorption coefficient and the scattering coefficient. Increasing glucose concentration decreases these coefficients and shortens the optical path, which consequently increases the light intensity. This can be depicted in this figure. As you can see, the angles of bending in the incident light on the tissue with less glucose is more than the one with more glucose. Mid-infrared spectroscopy is based on the same principle as near-infrared spectroscopy. The major difference is that the beam of light that is focused is within the 2500 to 10,000 nanometer spectrum. An example of a sensor that uses mid-infrared laser spectroscopy is the attenuated total reflection sensor. It was enhanced to become non-invasive. One of the enhancements is the flattened area. The effective optical path length of the flattened area enhances the sensitivity when compared to that of a straight fiber ATR sensor. Another significant enhancement is the silver nanoparticles that increases the infrared absorption of the sensor due to electromagnetic and chemical enhanced mechanisms. The electromagnetic enhancement mechanism states that the field intensity generated by incident light is coupled with the metal surface, and the local electric field on the silver nanoparticles has an increase. The chemical enhancement mechanism states that the absorption coefficient of molecules has an increase because of the chemical reactions of the absorbed glucose molecules and the silver nanoparticles. These quantities can be found in the infrared expression here. The advantages the sensor has over common biosensors for continuous monitoring, which are the sensors listed above, is that it avoids the effects of the body's bioelectricity, significantly reduces the signal drifts, and improves the accuracy as it works based on optical signals. And secondly, no glucose depletion occurs during the detection, as detection is done by 5 emitted wavelengths near the glucose absorption peaks as opposed to the specificity of an enzyme. Here are the references consulted for this presentation.